So basically, guys, this is very, very important. Oh, my thought, so cool, my thought. So basically, I need to do this properly now. This video is for the model on the system model, sparse security model. Basically, we have to do this properly, because if I do wrong, I don't get it right. So, yes. So this is sparse security. What's sparse security? So basically, this is sparse security. And be more formal with this video. Sparse security model. So basically, you got like dimensions of security. You got to trace and ensure that no one can get it. But it's about signal versus noise fidelity. What is the signal? What is meaning? What is knowing? But it's basically based on 4D tensors instead of 4D and above, like 4 plus 4 is 12, 8. 8 plus 8 is 16. 16 was dimension that's to calculate for a 4D security model to be perfect. But there's some sparsity in there. So basically, I'm building for the OBINexus legislation. Today's date is the 1st of December 2025. OBINexus. Sparse security, what is it? So basically, you don't know how you're going to get attacked. That's like the thing. You can have an attack, offense, or defense. But once someone comes to your company, just become their hostile already without you knowing. So that's what I'm saying, just a silent threat in waiting for you to attack. So the thing about this model, you have to ensure that the dimensions align with the intent. So let me give you the overview of sparse security model. So we got attack, defense, and offense. Attack, defense, offense. Those are the three main categories of security: cybersecurity, offensive, defensive, and attack. And then we got what 1D. One dimension. So you get one dimension of security, which is a linear security model. Two linear, but my one works on OBINexus derivative tracing system. The tracing of characters, the patterns in the system, via the Rift R syntax, Rift regular expression. 1D, one dimension, just a line. Line, infinite line, broken. It's already broken. You're already observing it. A line. What see. But in the answer view, it's just a perfect security. They never can come to that line, so they don't have to come to security because it's just a line. It's a line segment. So it's been, 2D, height and width. The 2D box, 1D circle, 1D circle. It's just infinite. It's perfect. And then you get the area. They can protect something in the area. Now the 3D one, you can get someone in here. You can protect forever. Tarek, give me money. 3 times 3. So basically, the sparse security model is modeling interdimensional threats. But if you go to my QFT repository, github.com/OBINexus quantum field theory, you should find the QFT threat modeling for this kind of model too. But sparse security model. So basically, sparse just means you can be modeled anyway. You can give it any information and will resolve itself. Automatically. It has to resolve based on some seed it already knows. Basically, if you put an algorithm, the algorithm can run the code. So basically, I can type in some numbers, like something. I can put in. Basically, it's a 2-to-1 mapping for it. So I can create a perfect scenario right now, but I don't want to think about that. I'll think about that next time. Perfect security model. But it's basically for threat modeling for evolution that computers can do it. So out of the loop systems, AI systems. So you get one dimensional line, a 2-dimensional box, a 3-dimensional cube, and so forth and so on. Same for the sphere, a 3-dimensional sphere. It's not a 2-dimensional cube, a 3-dimensional, 2-dimensional circle, and a 1-dimensional thing. But they're under lattice transformation. Lattice transformation just means a union. Union. Union basically two sets. Think of it as add the two union, disjoint, and disjoint property, and what the intersection properties for systems. For example, 3 numbers. 3 plus 3 plus 3 is 6. 9. 3 plus 6, 36. 9. Because life, work, breath. And then you have the other one. But you go 3 times 3 times 3 equals 27. 27. 27 plus 9. 36. I get 36. Minimum dimensions I have to protect based on my frame of reference. Because I'm a 3D world. For myself only. But the problem with this model, because I can break this model into 2D, 2D, it's from a 2D beam. So I can say I want to come to security place that has some information in a bubble. So basically, I can say I want to project some of infrastructure. I'm a 2D one. So let me try and compute it basically. So for me to project into the real world, I'm a 2D being, not 3D. I'm 2D namely. I have to say that again because you guys are not following me. 2 plus 2 times 2 is 4. 2 plus 2 is 6. 2 plus 2 is 4. So I get 8-dimensional vector. 8 dimensions. Basically, I get 8 inputs. I can run 8 inputs to output based on my model of 2D model. So this is just the pattern matching method I'm calling. So you get 2 plus 2 is 4. 2 times 2 is 4. 4 plus 4 is 8. 8-dimensional inputs. But my one here is 36. I need 36 inputs minimum to get it. But for myself, the minimum I need is just 2D beam. Let's say an ant wants to break out. Let's say a 2D ant wants to break out a circle and come to my 3D world. 2D ant, my 3D world. So what the ant wants to do is project itself. So 8 dimensions. 4 plus 4 is 8. 8 dimensions, 8 inputs it needs. But the ant knows 8 inputs is the minimum. So what about the maximum? What about new problems? He knows the 8 is the minimum. So you say, okay, I'm going to try to do the maximum. So if I need the minimum to maximum, what's the maximum I need? So it thinks about, okay, this is what I cannot do. You just flip the script. So I'm in 2D. This man doesn't have, works on, he doesn't really understand me. Kinematics. So he has 8 inputs that are vulnerable. So what this input, I don't know. I don't really care. So what the out has to do is this transcend. Now that 2D ant does this once we go 3D form. So what the ant has to do, he has to go 8 inputs. 8 inputs is fine. I can separate it into my 2x2 framework, making a map of 4 functions. So I have 4 functions maximums that are 2 that are homogeneous, like 4 that are homogeneous. That means they work on the same type of data, and 4 that are heterogeneous. And how to break out this box is literally doing this. 2 functions, define 2 functions, 2 functions n, 2 functions, so basically it has to create a functor, what I call a functor, an OBINexus functor that, I'm giving you guys an idea right now. Because, you guys have to get right in my security model. If anybody breaks that one, it's not my problem. You broke your own. But don't come from crying for me. So you get, I'm the model now. So you get 4 categories of it. So you get 4 models of it. So you get, so basically you get, so the answer a model. So you get 2 plus 2. To a function a and b, defined by a and b. But that function takes 2 inputs that are homogeneous because they need 2 inputs. A and b are functions. Functions a is a homogeneous and b is homogeneous, and they work on the laws of lattice intersection. That means where a and b unite, and then union negation. So an A and B. So how does it work formally in the framework A and B? So A and B are 2 functions. So how the A and B will do this? A, B. When you compose A, B, you get AB, or AB, or you can get BA. And the answer knows that AB is equal to BA, homogeneous. What the computer can process easily. But in the worst case, that would be the best case. AB equals BA. And there's just 2 functions composing. That is composing, and it's all mind. Just thinking about theorizing about it, just even writing it down. Just have a pen. So B equals AB equals BA. Because normally the input you put to AB, you get BA. So how this will work in the ANS view? So A has 2 inputs, but there are 4 functions you can define. 2 inputs. Let's call it input. Because let's just keep it numerical. Because that was 2 functions. So you get a maximum. So 2 inputs. So a minimum of 1. Basically, you can use a minimum of 1 input per 2. But it says, okay, I'm smart. I'm really smart. I'm gonna put 2 inputs into 2 functions. So it defines functions AB with functions AB with min, max. Because they're homogeneous, they take the same inputs. So A is like B is like B is like the same function as A and B, but it has a clamp. So this clamp is like AB is the same as BA. So what the AND does is flip the B to A. So B starts with A to B. So basically max to min. So B dot max is a functor that's what that prioritizes the B, the first input, first. The first input first. The B the max. Am I? This was basically what happens to the worst case of whatever the job is. The B the max, and then you get A the min. So A the min and max do the same thing, but they work in inverse. Inverse. So we end up with this here. Look at this, guys. We end up with ant A min max, B min max. But you can also put because you don't know this is basically the same input, but the input is not arbitrary or anything. But you can put an arbitrary input, something you don't know in there, like something like something that's not arbitrary. I mean, arbitrary means it's heterogeneous because it's a homogeneous model. Then this is one understand that you can put like a gobbledygook like characters there. That'll be homogeneous. But if it's just numbers, it's very structured. But that's homogeneous in its basically there's no heterogeneous data that you can't process. You can't put out information from because the input has to able to process it to return an output. If you can't process it, then it's just noise. Then it just it crashes, which it shouldn't do. So the AND has two inputs for each two functions. So that makes a total of 4. So A dot she can compose I'm very smart. I know how to do it. So it has to come from A. So you get a function AA. Okay, get A min. A min is a functor, a homogeneous functor that takes. I'm teaching you how to do functor frameworks now. A min, which is like small a. Small a is a small a because you get big A, which is the big A, the two A's. You get A min is the minimum it takes. A sub min. It works in two inputs. A and B to get 4. Just to get 4 minimum. 4 minimum 4. So A and B is two functions with no boundaries. No, just it can be just natural numbers. Just natural things that go between natural numbers. Because A min takes a number, any number, let's say any integer, anything that's a unsigned integer. There's no boundary to it, because it has to resolve itself. So it takes an integer, and this is put an A min unsigned int A min A min A min B min A and min B, and that's the function defined. But that's the homogeneous model. In the homogeneous model will be min A, which is ordered in the way the order specs it to be. And then the min AA, the second A would take the maximum first in the inverse order. Unsigned int max. Maximum, then unsigned int min. This is a framework I'm giving you guys, the functor frameworks. Now, A max and AB do the same thing, but they want to transcend my dimension. What comes to my dimension? So what you have to do is take this thing. So answer is 1. The 1 plus 1 is 2. 2D. So the answer we got are two functors, A and AA, that do the same thing equals big A. Now big A is it's homogeneous, so you have to work on the heterogeneous one. So the transcending into my dimension. So it now says, okay, I'm gonna take my dimension, I'm gonna clone myself, I'm gonna put myself into the 3D world, into your view. So this is homogeneous. So you can transfer myself and become a Marieless. You see, be like a moving a circle, just by itself. Just moving on a piece of paper. But I can't interact with its own existence. And it can observe me, but I can observe it, move it because it's bi-directional. Because I'm in a 3D world. So what I have to do now is now transcend. So it has one dimension to look at all the time. So it just says rotate this. So basically, I can literally define this function for you guys called clamp to observe reality. But clamp has to trace the derivative. So what the ant has to do now is to break out as whatever the dimension is circle to what? It's circle to what? It's circle to what? To our world. So this will take so you basically get half its dimension first. Half is dimension of this input, because that thing is straight lines. So basically, you see what I'm saying. So half of the minimum 1 plus 1 it has is 2. 1 plus 1 he can't observe is 2. 4. 4. So for it only, it needs 4 inputs, a minimum. But it says no, I don't want to come back to my reality and die, and disappear. Something break and don't exist. My whole structure, my whole form breaks because I'm an ant. I'm existed. So he has to add. So this 4 dimension. So if he has 4 dimensions, it can observe at all times. So he says, okay, I know I can observe this for 4 inputs at any time. So I need another 4 inputs. I still can observe them. because we're funny people. So what it does is this. Because we are related, so it's just lenses. So this is lens in one. So you have to define this 4 dimensions too. 2 plus 2, 4. That'll be 8 dimensions. So you have to have 8 inputs minimum. So to sustain itself in that framework. So that's 4D. So you don't want to die. So what the AND does is this. So you get 1 plus 1 equals 2. Which are homogeneous inputs for dimension. You get 1 plus 1 equals 2. That's 4. Then you get 2 plus 2 equals 4. Now 4 plus 4 equals 8. So you need 8 inputs minimum. So what the art does is this. Basically, if I can act on if the act has 3 minutes, it's the maximum of 8 because I can act on other 4 to stop it from coming to my reality. So he's 8. So it does this. So 1 plus 1 equals 2. So basically, it says, okay, 4 have to take over the 4 dimensions for the system. So the ant has to now do the same thing. Function ho has to function d. Function trans. Let's call the function f of function t. The big T for transcend has 2 inputs. Take 2 functions A and B that map. We would be next to so basically a calculated derivative of that traces. So if the ant was to be in my location right now on this piece of paper, it takes wherever the coordinates is of my reality, based on its frame of reference. So the ant will think, okay, my coordination is like on this grid, on this paper, it's going to a 30 centimeter paper, 30 to 15 centimeter paper. I'm at the center of his reality, center of his view. He's really annoying me. He's poking his eyes in my reality, and I want to tell him to stop. He does this. Basically, the answer is like an equation. So, 30 to, half of 30 is 15. 15 because relative, take its relative coordinate system, 15, 15. 15 centimeters squared is the half the area, and 15 centimeters squared is at the center of the center, based on radius it's in. But that's just because it's a circle. It's a grid paper. It's a accordion. But that's also stands. My reality is what? Sphere, a perfect sphere. So, like the Earth sphere. So he says, okay, I know where I am. So where's Namdi at? I'm gonna say I don't even know where Namdi is, but I know I'm gonna send this paper. So I'll project to his relative center of this paper, and that will be the transcendental process. So what the answer to define? The input 15 centimeters of my volume. So let me calculate for you guys. 15. There's my calculator just fucked up me. 15 times 2. So basically, you got 15 times 2. You get 15 times 2. 15 times 2 is what? 30 centimeters. Now, 30 centimeters times pi. It's 30 centimeters. That's like the 30 centimeters. The radius from me, because we're in a bubble, and the pi is just the dimension. The pi is the perimeter, defining the geometry, like the isometric parameter, because we're in a bubble universe. The perimeter is 3.14, so times pi. Sorry guys, times pi. Where's pi? Times guys, I don't want to die, guys. I'm just find pi dying. Guys, trigonometry times pi. Basically, it's gonna be 30 centimeters squared times pi. No, basically 15 plus 15 is radius. So you go through the 30 centimeters, 30 times pi, but don't see pi. Sorry guys, 30 times pi. So 30 times pi times 30. So basically, it's gonna be 30 times 5. 30 times pi. Because that's the perimeter of area. So in my reality, has to come into the 3 world, become a 4-row ant. So that's the perimeter he has to transcend, literally. So in the area view, he takes basically he has to take his own area. That's the ant's area. But you see, the ant is like in center, it's like half, like a 1 centimeter ant, or like a, let's say it's a 2 centimeter ant. Let's just be real here. Ants are not really the same one. Okay, let's say it's a half a centimeter ant. Half a centimeter. Half a centimeter is like 1 nanometer. No, 1 centimeter is very short. Okay, basically ant is like a 2 centimeters. No. Let's say an ant is a maximum of 1.5 centimeters. 1.5 centimeters. For it to come to my reality, it has to be extend its plane existence, project itself in the polar coordinate system towards my reality. 1.5 centimeters times 2 squared, obviously 2 pi r. You don't basically got 2 pi r pi r. So you're gonna do pi r. Pi r is like pi r squared. So you have to go squared. So so it takes its own 1.5 centimeters and then does 2 1 1.5 1.5 times 2 1.5 times 2 1.5 squared. So 1.5 squared 1.5 squared squared. So 1.5 squared. 1.5 times 1.5 squared. 1.5 squared. Wait, 1.5 times 1.5. Basically, you do 1.5 times 1.5. That's a square anyway. So that's 1.5 squared. It's the same thing. Then you get 2 squared. 1.5 times 1.5 is what? 5 times 5 is 30. No, 5 times 5 is 25. Corrected 2. 5 times 5. 5 times 1 is 15. 16, 17. 17.5 centimeters. 1.5. 1 times 5 is the same thing. 17.5 plus 17.5. And that's 5, 7, 8, 9, 10, 11, 12. 12. 12 and then 12 and then go 7, 8, 8. And then 18.5. 18.5 what? Area. So you have to take the volume of basically this volume is now 18.5 centimeters squared based on the so basically it's a big ant on a big paper. So if the ant is 1.5 centimeters if basically so basically if the ant's length is what? Basically this is so if the ant 1.5 centimeters in this domain, in my rate is 18.25 centimeters. Its perimeter only, its length. And its width is whatever the length width height, but it's not its height. It's just the length. Now that's a 1-to-1 ratio of it. So if the ant is what? As the ant is now 30 centimeters long, so that's the pi r radius squared. Now I can't even find the pi symbol, so let me go online calculator. This is my statistical calculator. I'm just go to the non-statistical calculator. So we get pi. No, I don't see pi here. So we get pi. So basically times pi. So if the ant is coming, it has to have this half. Basically, if the ant is like long, because I said its length is just 1.5. That means its width is just 1.5 as well. So that means that the ant is now in my room. I'm telling you, 18.5 centimeters. Centimeters is the length, just length of the height, but the width is the same. It's like a uniform because it's a uniform radius. So if I say the radius is 1.5, that must mean the ant has the 15 times 2. 15 times 2 is what? 30 centimeters. Now 30 centimeters is the perimeter of the perimeter. It's it's 1.5 1 unit of the, and that's the perimeter of the thing of the ant. Now that's 30 centimeters. 15 plus 15 is 30. So that's 30 centimeters. The ant is now. It's relative to my coordinate system, which is at half of the thing. Wherever it is. Basically, where's the ant located? 15 centimeters relative to me, which is the center of the paper, but relative to me, because it's not relative to you. So this is 15 squared. So if the ant is 1.5, this is just the perimeter. This is just the first dimension is broken through. So the ant computes all of this. 1.5. 1.5 at the length, width, and height. And then it says, I am meant to be 18.25 centimeters centimeters in length, and then the cubed one basically length how basically we have to work on 18.25 times 3. It's not basically if I'm 1.5 in length, I'm 1.5 in width and height. So 18.25 times to the power of 3. 18.25 to the power of 3, guys. Sorry, 18.25 plus 18.2 plus 18.2. Oh wait, sorry, plus 18.25 plus 18.25. That 18.25 is 5.475 centimeters mark. So basically 18.55 times 3. Why is this not doing this? Oh, this is like giving me the wrong reading. Reading. So 18.25 18.25 times 3. That's 3. So the ant now this is basically ant is like 3 centimeters in width, height, and length. But that's space and the centimeter model. So if it has length of width, it has a height of the ratio. So it's 3, but it's not like a square ant, like a kind of square ant. So I don't like that one because it's not really anti. So 18 plus 25 plus 18 plus 25 plus 18 plus 25 is what? 5, 10, 15. Oh, basically, 5, 8, 5, 10, 15. Carry the 1, 4, 5, 6, 7. 7, 16, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 25, 1, 1, 1, 3, 4, 5, 3, 4, 5, 55, 55.75 centimeters squared. So 55.75 centimeters squared is what? Where the ant's dimension is. So it's basically that is a volume of 55.75 centimeters cube in my real world, and that ant is like a very big ant. so basically I'm really giving you the information why functional framework. So the ant control, that's my volume. That's what it should be. It's from 1.5 centimeters here in width, height, and length. That's the same as my relative of 18.25 centimeters. I should be is cubed volume based on the volume model. Because it's a 1.5, just a scalar. That's a linear system. But the uniform one is just 18.25. So that answer knows that. So it says, okay, fine. I now know what I've got to do. So for this to work, I should never pop. So basically, you get 2 inputs minimum. So the answer is what? So the ant comes to my research. Basically, my 1D ant then says, oh, I don't want to be in 2D world. I don't want to be a paper. So he said, just a line. Let me come to reality. Let me come to a box. I said, he says, okay. My area is what? My area is so basically, it has to preserve itself 18.25. It then defines OBINexus derivative function of DA, DB, and DC with unknown. So basically, the goal of this is a security model for the whole system I'm building. So the ant comes into my rater, but what would undo? So the ant just comes in. When I walk in my room, I don't really care. But I'm just gonna chill in your room. I don't care no more. I don't be 1D. You can go 1D. So that's what I'm saying. So I'm saying to you guys, what will happen now is the ant has to have the functions, the heterogeneous functions, which are based on the sparse inputs. So you can model it anyhow. So it knows how to model it. So if you have like 2 functions, A and B, one function that take 2 inputs, 2 functions that are homogeneous. It then looks at the minimum ways into do it. So it goes down. So 1 plus 1 is 2. 2 functions that takes only 2 inputs. One more function each. You get 2 inputs. 2 inputs to 1 function. Then you get another input that I cannot act on, that he can act on. So it's okay, I want to action everything because I know there's no threat there. I'm not there. Then 2 plus 2, it gets another 2 inputs. It can it's a 2-dimensional, but he knows my mixture is 3 by 3. So he gets 4 inputs minimum he can act on. But then he knows that this 4 input is not good enough. But it's 4 inputs doesn't mean equal 4 dimensions. They mean 3 dimensions. So it says most of my one 3 plus 3, 6. 3 times 3 is 9. 9 plus 6 is 15. 15 inputs I need. So it says, okay, this 4 inputs is not good enough. So I need to have 15 inputs. 15 inputs. So it says my 4 inputs is not good enough. I know that now. So it says because he's got 3 dimensions, 3 actual dimensions between himself. So 15. So I have to think about 15 inputs model. So the 15 inputs are there. So what would undo with these 15 inputs? It says, okay, I need 15 inputs. So what can we have 15 inputs to get into the zone? His life. So he gets this. Basically, he needs 6 inputs minimum. It's basically because 3. I can IK and IK K, and then this is basically the ant knows he can only act on 6 inputs. So the ant knows he can only act on 6. Why? Because if I have 6 dimensions that I am from, the 3D I can exist without a problem. He has 3 dimensions he can't act on. You know, 3 other dimensions he cannot act on. So 3 other dimensions you cannot act on. Why? Because the 3 other dimensions, basically, if I have 6 dimensions you can act on, there's one-to-one mapping of that. On my dimension I cannot act on his dimension. So he says, okay, I want to take 6 inputs because I now know 6 inputs. Now he says, B has 6 inputs defined across all the stream. So it has like 6 inputs. So from now, instead of 2 inputs, it has 2 minimum. So basically, 6 maximum inputs, 6 minimum allowed per one domain. So since I'm very smart, I'm gonna have 2 inputs. So I'm gonna have a sparse model. So I'm gonna have A take a boundary, or A is gonna translate A min max. Gonna work on the minimum maximum of where I wanna be. B is gonna work on the minimum and the maximum to minimum. I'm gonna B, but then we have a function called C. Now C now works on the same thing. Basically it's gonna try to climb by location. So basically this one's gonna, the first function A defines the where the position of the the position x position, then B is the y, and then the z is the z. So let's call it a z y z, a y z. But you can name everything. So I'm gonna be in this coordinate, but this is not good enough still because Namdi. So this is Namdi very smart. So if the ant wants Namdi there, it has 6 min max. This is XYZ coordinate system. So this is gonna project the ant into my reality. So basically, just look at data x dot min, x dot max. But that's what the ant's frame of reference is. So this works for the ant just fine, because just 2 inputs it needs, and it doesn't need to know my inputs. If it never knows my inputs, you have to store it somewhere safely so I can access it. So you change also, the ant changes itself. Say, okay, this is not good enough for me. Let me do my way. So what the ant does is define 2 functions x dot min. So it's gonna work on the minimum functions, which is 6. X the main, which is the same function as x is a property. So basically, if x is a functor, min is the property or the input. Based on this can be again 15 centimeters, just numbers. 15 centimeters based on latitude model. Like center 0 0, just its own way it is. But if this x is a min, that must mean very important guys understand is this min can be return an x. Return an x. So that's the problem the ant is saying. So the ant has to make sure that I don't get involved. But we'll come back to that later. So if x dot min is the minimum input, x dot max is the maximum input, and vice versa if they're functors. So if it says, okay, the max, so basically defines them as max x, the boundary is max x. So basically the other ones is allowed. So it defines a total of 6 functions. X dot min, x min x, min x, min x, min x, and then max x, which are